Hello, everybody. Friendly neighborhood calculus teacher, this guy, back again. We're going to look at topic 9. Topic 9 is a BC calculus only topic, and it is on polar. So it's interesting. The unit 9 on parametrics, vector, and polar are often assessed as separate free response questions. But that's nice because that gives us a chance to review a very different kind of math. Those polars, parametrics, and vectors are pretty different from what we normally study. So when we're looking at polar for problems like this, don't worry, I will encourage you to do it in just a minute. The types of things that we tend to focus on, and this is not a comprehensive list, just a list to get you started, would be working with polar coordinates and intersections. So r, the distance from the origin out here, wherever the curve is. Theta, whatever rotation we would be if we were going around the unit circle. We look a lot at area, area between curves, area inside of a curve, area outside of a curve. We need to remember these two super important conversions to go from rectangular to polar or polar to rectangular. Another thing we need to keep in mind with polar is there's all those different derivatives. There's dr d theta, dx d theta, dr dx, all of those types of things. And we want to be really careful and remember that something like dy dx is always referring to the slope of the path or the slope of the graph or the slope of the curve, which is not the same thing necessarily as, say, a velocity. R, again, and yes, I know I'm repeating myself, is the distance from the pole or origin to the curve. It's really important that we remember that because, again, polar is very different from the rectangular system we're used to. Some topics that kind of sneak in here are related rates and implicit differentiation, and horizontal and vertical tangents, equations of tangents lines, that kind of thing. So here is the question I would like you to do, and as per usual, give it a go first. This one is calculator permitted. I will be picking up soon with my work, and then we'll talk about the scoring guidelines. So I assume you've paused the video, tried the problem, took you between 15 and 20 minutes, and you have work that to some effect looks similar to mine. So in part A, we're tasked with finding the area of R. R is this region right here, bounded by the curve and the x-axis. So I'm finding a polar area, which means I want 1/2 r squared d theta. And I'm going to go from 0 to pi over 2. How do I know it's 0 to pi over 2? Well, it actually indicates we're going from 0 to pi over 2 like this, but because I had a calculator, I still double checked my graph. If I didn't have a calculator, what I would have done is I would have taken 0. I would have substituted 0 into here. That would have been 1 plus 0 times 1, which gives me 1. And then at pi over 2, 1 plus 1 times -1, which gives me 0. So I could have verified it without a calculator too. Anyway, we get this. You're not integrating this without a calculator though. So you can do this in either polar mode or rectangular mode. So I got 0.648. Part B, we want the ray theta equals k that divides S into 2 equal regions. Fortunately, we don't have to solve this one. So the region from 0 to pi over 2, represented by S, is 2 cosine theta squared minus 1 plus sine of theta cosine of 2 theta, that quantity squared, d theta, from 0 to pi over 2. How do I know that? Well, I looked here, and I said, either graphically or again checking points, that this corresponds to 2 cosine of theta, which is g. And if I look at my r to here is bigger than r to here. So I know that this is going to represent a bigger area. So it's this curve's area, the total area, the semicircle, minus whatever you want to call this shape, a lumpy circle. Who knows? So that's the total area. And half of that area is from 0 to k. So I chose to do it as double this area from 0 to k, but you could have also done it with a different ratio. You could have said 1/2 times 1/2 or 1/4 of this. We'll see the answer key has a few other options. Part C. W of theta is the distance between the points on F and G. So that's this distance here. Remember, R extends out from the origin out to here. So it hits both curves here and here. So it's this distance right here. So it's, again, this value minus this value. So that's how I knew it was 2 cosine of theta minus the 1 plus sine of theta cosine of 2 theta quantity. So the average value is integrate this from 0 to pi over 2, divide it by the difference between pi over 2 and 0, and then I got 0.45485 rounded accurately to 3 decimal places, and I stored that. Why did I store that? Well, because I had an idea of how the problem works, but honestly, it never hurts you to store a value. Like, you could have stored this too. But just be careful, don't store both of these as, say, A. Anyway, part D. Using part C, find the value of theta for which W of theta equals W sub A. Is this function W increasing or decreasing? Well, we know a function is increasing or decreasing when its first derivative is positive or negative, respectively. So that's going to be our reasoning. The question is, which is it? Well, in order to figure that out, we actually need to know the value of theta where this is true. So we want the average value, which we got from part C, to be equal to W, the equation that we also wrote in part C. And I solved this exclusively on my calculator. I did not do it in radian mode. I switched back to regular rectangular mode. And then I looked at, I think I actually subtracted this from both sides. So I had this minus that. And then that was my 0. I stored this. I substituted it into the derivative. I did not write out a formula for the derivative. The problem didn't tell me to. I have a calculator for this question. I just used option 8 on the graphing calculator at the stored value. It gave me negative 0.582. Consequently, W prime is negative, so W has to be decreasing at the value that I got. Continuing and finishing here, the scoring guidelines. I know you saw the scoring on my work too, but I think it's useful to see the scoring guidelines as well. So we have 1/2 r squared d theta, same value, accurate to 3 decimal places, 1 point for the correct polar integrand, 1 point for the correct answer to 3 decimal places. Here are a couple of other ways to write when the area is divided into half at K. Here is a slightly different way to write the average value here. So it was 1 point for this function, 1 point for this integral statement, and 1 point for the value rounded to 3 decimal places. For part D, that was 2 of the 9 points. We take our W from here, set it equal to our value from here. Got 0.518. Notice how they didn't specify what the value of W prime of 0.518 is. All they did was say W prime of 0.518 is less than 0. Further emphasizing that, especially for calculator questions, if it doesn't say antiderivative, write it out, or derivative, write it out, don't take your time and do it. If it helps you to do it, I guess do it, but I feel like time is potentially going to be at a little bit of premium here, and you're going to be better off taking a moment to reflect and check on your work. That is it for topic the 9th, the polar style FRQ questions on the AP Calculus exam. See ya.